This week's JavaScript program is a large-scale one, no fewer than 236 lines of JavaScript code. To demonstrate how agents cooperate to solve a problem and communicate via a blackboard, I have chosen an example that naturally lends itself to this approach, namely Sudoku puzzles. I assume that you're familiar with Sudoku, so I won't waste your time by explaining it. If you're not, then I envy you. You probably lead a rich and meaningful life. The program overlays the 9x9 Sudoku grid with 27 agents, one for each column, one for each row, and one for each of the 3x3 blocks called NonUS. The blackboard part of the program is the Sudoku grid itself, since the numbers written on that grid are the triggers for the agents, and any changes made by those agents are written back to the grid. The agents are lined up waiting to act, and every time a change is made to the grid, the agents for the appropriate column, row, and nonnet are triggered and added to the end of the line. Well, in fact, any change in the grid only triggers 2 more agents, as it must have been one of the 3 that made the change in the first place. If an agent tackling one of the rows alters a grid cell, then only the agents for that column and nonnet are triggered, and so on. Initially, agents are added to the line at a rapid rate. As more and more numbers in the grid are identified, and the rate at which changes are made, the fewer and fewer agents are added, and the line rapidly shrinks. The game ends when there are no more agents in the line to activate. You can see the screen in play here. A table with a border is used to display the grid, and in fact, rather than produce many nearly identical lines of HTML code, I use a trick and get JavaScript to set the HTML up. Here it is. Each cell in the outer table is an HTML span named from N0 in the top left corner to N8 in the bottom right. This outer table has a fairly thick board around it to highlight the nonets. Then the function setUpTable is called 9 times to create the individual nonets in each of those spans. The function builds up the HTML code to display the nonnet in a string variable called s. I always call my string variables s because I have such a powerful imagination. The code takes the form of another table, this time with a thinner border, and 3 rows of 3 columns each. To start with, the board is blank, waiting for the viewer to enter the numbers that make up the initial puzzle for the agents to work on. So the contents of each of these 9 cells is another span, which contains a drop-down selection list. The viewer can select any number from 1 to 9, or leave the cell blank, the default value, specified by the NBSP, or non-break space character, which is the first item on the list. Once the code for that nonnet has been created, the string variable s is copied to the span in the outer table, and the nonnet appears on the screen. This is probably a good moment to introduce you to the global variables we are going to need throughout the program. The grid G is a 2-dimensional array, with the first dimension representing the row in the grid, starting from 0 at the top, and the second dimension representing the column, starting from 0 on the left. The line of agents is stored in the array Agents, with each agent being given a number from 0 to 26. The agents numbered 0 to 8 handle the rows, agents 9 to 17 the columns, and agents 18 to 26 the nonets. So the line of agents is essentially a 1-dimensional array of numbers. The number of agents waiting in line is stored in NumAgents. The program has 2 modes. You can solve the problem one step at a time by clicking a button, or set it to run automatically with a delay, currently set at 2 seconds, between each step. The variable continuous is set to true to get the program to run by itself, or false to run one step at a time. The variable time is used later on during continuous running. 3 variables, called row, column, and nonnet in uppercase letters, are set up for convenience, so that we can distinguish between the different agents called. You'll see these popping up at various places in the code. Then we come to the arrays RIMP and CIMP. There are 3 types of agents in this system, for rows, columns, and nonets. However, they all function in the same way, and it makes sense to use the same code for all of them. The only difference between them is that the 9 cells in the grid they examine are in different positions. The row and column positions of these cells are passed in arrays RIMP for the row numbers and CIMP for the columns. The 2 examples on the screen show the arrangements for an agent handling the 4th column or the 6th nonnet. Once the viewer has entered the initial figures in the button, there is a button that fills in all the other cells with all possibilities. It does this by detecting blank cells in array G and simply filling them in with the digits 1 to 9. The idea is that as the puzzle proceeds, the program will whittle away at these cells until all digits are found. The function displayCell updates the appropriate span in whichever cell it is by putting the new contents in separated by line breaks every third digit. There are two more buttons, one to run the puzzle one step and one to run it continuously. In fact, they both call the function one step that makes the first agent in the list do its thing, but in continuous mode there is a timeout statement at the end of one step that calls the function again after a delay of 2 seconds, 2000 milliseconds. Adjust that figure if you want the program to run more quickly or slowly. You'll see that setting up the puzzle has also started a line of waiting agents. This is because the function setUpPuzzle calls function lineUpAgents for every value the viewer enters in the grid. Function lineUpAgents adds 3 agents to the line for every value entered, one for the row, one for the column, and one for the nonnet. Function addAgent only adds an agent to the line if it is not already in there. Otherwise the program will take twice as long as it does to solve any Sudoku puzzle. Those mathematical expressions turn a column and a row number for a cell into an agent number. The rows have the same numbers as the agents, and the agents for the columns are 9 more than the column numbers they tackle. The tricky bit is converting a row and column coordinate into a number for the nonnet. I'm not going to go through the maths on this, you'll have to sit down and do that for yourself. But whenever the program refers to a nonnet, you'll see something similar in the code. The floor function in JavaScript's math unit rounds any decimal value down to the nearest whole number below it. You'll notice that the last line of function addAgent also adds the agent to the text area Agents, which lists the agents waiting on the screen. The function getAgentName turns the number of an agent into a word, row, column, or nonnet, followed by a number. So agent 0 is displayed as row 0, and agent 19 is displayed as nonnet 1, and so on. The function oneStep takes the first agent off the list, if there is one, and runs it. If the list is empty, then it reports a "sorry, no more agents" message. In fact, it also displays this message when the problem is solved. That's something you might like to change. Having extracted the agent, it decides whether it's a row agent, a column agent, or a nonnet agent, depending on its number, and calls the appropriate function to run it. Once the agent has run, if the program is in continuous mode, a timer is set up to call one step again after the 2-second delay. That's the purpose of the global variable time. The next agent to run is found as the first element in the array agents, the first person in the queue if you like, and it is copied into the variable nextAgent. This is the value returned by function getNextAgent. The lines after that simply shuffle up the agents to remove the agent from that line. After that, the name of the agent is copied into the input field on the screen to display it in the spotlight, and the list of waiting agents on the screen is also updated. The functions to run row, column and nonnet agents essentially do the same thing, as they all call the function runAgent at the end. However, before that, they make sure that the arrays RINP and CINP are set up by copying the appropriate values from the grid into those arrays. The complicated one is the nonnet version, of course, with more of that arithmetic based on the number 3. There's that function math.floor again, and I also assume you're familiar with modulo, represented by the percentage sign. This performs division, but gives you the remainder of that division rather than the quotient itself. We do need to pass the type of the agent to the function runAgent in the form of the global variables row, column, or nonnet, so that it knows which agents to add to the list if it makes a change to the grid. There are 2 basic tests to be carried out on rows, columns, and nonnets. Firstly, if the contents of a cell has been isolated, then any other cell in that group that contains the same digit has to have it taken away. In this example, the 2 and the 8 have been found in the nonnet, so those digits must be removed from all other cells. Secondly, if a digit only occurs once in the row, column or nonnet, and that cell also contains other digits, those other digits are removed. For instance, in this row, only the last cell contains a digit 9. The other digits should be removed from that cell. The function runAgent divides into two parts, one for each of those tests. Function runAgent does all the heavy lifting in this program. Here's the first part of it. A loop goes through every cell in the group being considered. There are 9 of them, of course, and the contents of the cell are copied into a temporary variable temp for convenience. Note that the indices of the grid cells copied are themselves the values in the array rinp and cinp, arrays within arrays as it were. The first test to be done is if any digit has been found in a group. A single digit in a cell will be in the form of a string of length 1, and if such a digit is found, then the function must go through all the other cells in that group, removing that digit. This is done by nesting another loop inside the first one that goes through all the cells again, and if it finds the digit temp in any cell apart from the one where it's known to be, then it's removed. Since the digits are stored in the grid cells as strings, the one in question is found using the indexOf method associated with those strings. If the digit is present, this will return its position with a number from 0 upwards, and the digit can be removed from the string using 2 substring operations, just like snipping a frame out of a reel of celluloid film. The screen is updated and a brief description is added to the text area Results, telling the viewer exactly what change has been made. Since the grid has changed, we have to add agents to the line. This is why we need to pass the agent type to runAgent. If this is a row we're dealing with, we need to add agents for the appropriate column and nonnet only. Similarly, if it's a column, we need to add agents for the appropriate row and nonnet. The second test is a little more complicated and is a 2-stage process. Firstly, we need to count how many times each digit appears in the row, column or nonnet. A temporary array count is set up. Please note that this array will need 10 elements, not 9, since array elements are indexed from 0. With 10 elements, element 1 can contain how many times 1 appears in the group, element 2 how many times 2 appears, etc., up to the last element, element 9, which will contain how many times 9 appears. Having determined the counts of the digits, we can go through the group again, looking for digits appearing only once. If 1 is found, the count for that digit is 1, then we go through all the cells looking for the only cell that contains that digit. If it also contains other digits, i.e. the string length for that cell is bigger than 1, then the cell can be set to the digit in question, the appropriate agents added to the list, and the display updated as before. There, that's pretty much it. I was surprised at how little explanation was needed for a very long and involved program. I'll finish by just showing you the function to add the appropriate agents to the line. This is very similar to the function lineUpAgents, except it only adds a row agent if the agent being processed isn't that row agent already, and similarly for the column agents and nonnet agents. The puzzle was a textbook example of Agents and Blackboard. The initial problem is written on the blackboard, i.e. the puzzle grid, and the appropriate agents are lined up. Each one acts in turn, writes any changes it makes back to the blackboard, and wakes up further agents from their slumber before going back to sleep itself. Of course, the program given here is only very primitive, and not just for the reasons I've already mentioned. It can solve just about any Sudoku puzzle you might find in a newspaper, provided that puzzle is marked easy. If it's marked difficult or challenging, then you might find it runs out of options before all the digits have been found. Those of you who are keen on Sudoku might consider adding a more sophisticated solving strategy to function runAgent, so that it can solve those puzzles as well. Also, you might well be familiar with Sudoku's 2 unknown relatives, Greater Than Sudoku and Killer Sudoku. It will be interesting to see Agents and Blackboard programs for those variants of the game. If you're not familiar with them, might I give a shameless plug and introduce you to tutorials I have on my other channel? Just saying, just saying. That's the end of the video. Please do click on the like button and subscribe to this channel if you would like to hear more from me every week. Also, if you do download the program from my website, link below, and tinker with it, I would be interested in hearing how it went, so why not leave a comment below? Thanks.